Miss Wallace teaches chemistry.
Today we are going to look at electrolysis. It's a lot of theory behind it. We only have one calculation that we need to do, just a lot of theory and understanding. So we're going to get the theory out of the way first, and then we're doing mole calculation with it. So mole comes back. Okay. Alright, so as it says, electrochemistry is the study of electrochemical reactions. The study of electrochemical reactions. And for these reactions, they can either produce electricity, right? Or they can allow electricity to pass through them. Or in other words, they need electricity to proceed. Right? So, once again, for electrochemical reactions, dealing with electrochemistry, they produce electricity or they need electricity for them to occur. For example, if we are going to create some form of salt, we have to dissolve it in water, and the electricity helps it to proceed, helps the reaction to proceed, or it makes the reaction proceed. Similar to when we're looking at rate of reaction, we need some form of temperature to be added for it to continue. So for these reactions, you include electricity so that it can proceed. Alright, now electricity is a type of energy. So you have heat energy, light energy. Electrical energy is one of those forms of energy that we have. Now for electricity, it results from the movement of charged particles. Right? And electricity cannot flow without any charged particles at all. These charged particles can either be ions, right? So Na and Cl ions. And when I'm saying like this, I'm not talking about your NaCl salt. So if it's a salt, it's a crystal, it's bonded together, electricity cannot pass through it. But if it were to be dissolved in water and it's aqueous form, it's ionized. So now these ions allow electricity to pass through them because they are charged. Similar for electrons, if you remember metallic bonding, electrons being delocalized. And we have free electrons going around, such as in a copper coin, zinc, aluminum. If you have free electrons going around, then an electric current is able to move through it. Alright? Now for electrical conduction, you have two types. They're classified based on their ability to conduct electricity. So you have the conductors. These are substances that allow electricity to pass through them. For example, aluminum, copper, zinc. You can think of any others? Yeah, any metals. Any metals allow electricity to pass through them. Some other examples, we have said the metals. We also have we'll look at these two. So we have graphite. Now, covalent compounds are non-conductors. You're going to see it here. Covalent compounds are non-conductors. Graphite is a covalent compound. It's a bond between several carbon atoms, so it's covalent. However, graphite allows electricity to pass through it because it has free electrons. Remember that structure? Yes, so it has an extra electron present in the structure that's not bonded in the hexagonal structure. Yes, so it's able to move around, it's able to conduct electricity. So for example, your pencil, they have graphite pencils, those can conduct electricity. Yes. Alright. Next we have our aqueous solutions of ionic compounds. So solid ionic compounds, as I had said, they cannot conduct electricity because they're held together. The ions are in the crystal, that is, they're not moving around freely. But once you put them in water, the ions are they're free to move. Right? So that's why we say aqueous solutions of ionic compounds. Aqueous means to be dissolved in water. Right? Then we have acids and alkalis. Most acids and alkalis, for us to even have it as an acid, we have to dissolve it in water. And once we dissolve it in water, it's ionized. So acids and alkalis, right, they're in aqueous, they're in water, so these are able to conduct electricity, especially the strong ones, especially strong acids and strong bases. For molten ionic compounds, now these are just the melted form of your salts. So think about volcano. And you know the magma coming out is in its liquid thick form. So think about sodium chloride could be similar to that, molten. Although it has a very high boiling point or high melting point rather, it can have a state similar to that. So when it's in its molten form, it's in its liquid form, liquid can freely move, so it can conduct electricity. Now for non-conductors, it's the opposite. These do not have electric current to pass through them. So for example, it can be solids, liquids, or gases. And the prime examples being covalent compounds. So all covalent compounds cannot conduct electricity except graphite, and you're going to learn about water very soon. So water it can slightly conduct electricity. So you know, so you can put some
Slightly.
Alright, it's a partial conductor.
Because you have the hydrogen.
It's not just because of the hydrogen. Alright, you know that hydrogen is a non-metal, right? So hydrogen and oxygen covalent bond. But for water, I'm going to explain it soon. Alright, so for here, as I said, covalent compounds cannot conduct electricity except graphite and water. Leave it at that. Other examples, here we have non-metals except graphite, plastic, solid ionic compound. So plastic is a non-conductor. Solid ionic compounds as well. We also have our covalent compounds and aqueous solutions are covalent compounds. So no matter if you dissolve covalent compounds in the water, still can't conduct electricity. They are non-polar, they can't. They have the same partial charges, not even partial charges. There is no form of polarization happening in covalent compounds. I'm going to have to go over that with you one of these days. Aqueous solutions of covalent compounds also don't conduct electricity. And so we have some other examples here. We have rubber, we have wood, and we have glass and plastic. Those are non-conductors. So here's an activity. We need to classify these substances as conductors or non-conductors. So tell me, what's the first one?
Conductor.
So conductor. Solid NaCl.
Non-conductor.
Non-conductor. Copper sulfate solution.
I said a conductor.
It is. Want to see something about a salt? This is a salt. Copper has a 2 plus sulfate 2 minus. That makes a salt. Acid and
It is a conductor.
it is a conductor.
So that.
What's next is that we're going to look at electrolytes. And what electrolytes are? These are substances which, when they dissolve in water, they ionize and can further conduct electricity. So for example, I have my salt. I have my solid salt. I put it in water. It ionizes and therefore it can conduct electricity. So I have 2 definitions here. First one, an electrolyte is a substance which conducts electricity when dissolved in water. Right? An electrolyte is a substance that produces ions when dissolved in water, which allows the conduction of electricity. Alright, just remember that electrolytes, these are substances which when we put them in water, they ionize, which further allow an electrical conduction. Right? That's an electrolyte. Okay. Now, in addition to this, it's also a substance that decomposes when an electric current passes through it. Metallic conductors. Now, for metallic conductors, this is something that you should know. And when you're thinking about metallic conductors, think about metallic bonding. Now, if you remember, for metallic bonding, they have free electrons going around, which allows them to conduct heat or electricity. So in the case of electrolysis, notice that for metallic conductors, they contain mobile electrons. They contain free electrons, right? And for unchanged chemically. There is no change with the metal. Now, an important note is, for example, copper, as I had given the copper example earlier. Like this copper, I guess I could probably use iron. Fe2 plus Fe3 plus. Now, when an electric current passes through metallic conductors, yes, we see a change. So, for example, we have rusting with iron, just an example, right? There's a color change seen. Similar for when we have, and this is rusting with iron, we go from Fe2 plus to Fe3 plus. It's very similar for copper metal. You have the copper, the brown copper, which is the copper solid, going to brown, going to its 2 plus form, its ions, and its ions are blue. Now, yes, there is a change, a visible change, but the only thing that is really changing is the number of electrons present. That's the only change. It's not a chemical change. We're seeing a change, yes, it's not a chemical change. The only change that happens for metallic conductors is the amount of electrons present. They're not broken though. We can't break them copper in a one simpler form. Right? This is just a change in its amount of electrons. For electrolytes now, they contain free ions. So metallic conductors have free electrons, mobile electrons, but electrolytes have free ions. Remember that when they dissolve in water, the ions are free, right? Now for electrolytes, they have chemical changes. So some form of chemical change occurs. Remember, for decomposition, you're breaking apart the compound. So for instance, it could be that you put sodium chloride, the solid, in water. Once you put it in water, it is going to break apart into its individual ions. Note the difference. For metallic conductors, we only change the electrons, but for electrolytes, we're changing, right? We're breaking down to form ions. That's what we're doing for electrolytes. Just remember, metallic conductors contain mobile electrons, while electrolytes contain free electrons. While metallic conductors, they remain chemically unchanged after the electricity is passed through it, while for electrolytes, yes, they decompose. There's a chemical change occurring. Something I had forgotten to mention is that looking at our graphite structure here, right? Now, so for free electrons, right? So graphite, it's not metallic. Graphite is not a metal, but remember that it's one of the only compounds, covalent compounds, that in fact conduct electricity due to its free electrons. Remember that carbon is it's in group 4, it's able to bond 4 times. That's carbon. But in graphite, it forms a hexagonal structure where each carbon is bonded 3 times, as you can see here. So this carbon right here is bonded 1, 2, and there would be 3. Each carbon is bonded 3 times, right? So therefore, there's an extra electron remaining for every single carbon. And that electron goes around freely inside our hexagonal structure. So that's why graphite is actually able to conduct electricity, similar to how metals conduct electricity. That's what I wanted to say. You have a question, Abby?
Can you explain that again?
Explain it again. Okay. Carbon, remember when you're looking at bonding, it happens based on the number of valence electrons they have. Carbon has 4 electrons and it's a non-metal. If carbon were to bond with itself, 2 non-metals as a covalent bond, it would have to share 4 electrons in order for it to be full. This carbon have 4. For it to have a total of 8, it would have to share 4 electrons. Not to be with the same carbon, but you have to share 4 of its electrons for it to be full. So it has 4 free spaces to bond. this carbon here. Right? This carbon. Each of these angles, they represent a carbon, right? And each of the lines represents a bond. So we have one bond here, so that's one electron from this carbon, one electron from this carbon. There should be another one there as well. It's a continuous structure. Okay. Yes, it continues. So as you can see, 3 electrons are taken up and we have 1 electron remaining. That electron moves around freely throughout the structure, carrying the electricity with it. Yes. Now, the strength of the electrolyte depends on the concentration of the ion. It's very similar to when we have looked at strong and weak acids and so on based on their ionization. But in this case, we're looking at the amount, the concentration of the ions, the amount of ions present. So for strong electrolytes, they are fully ionized when dissolved in water, and we have a lot of their ions present. They are fully ionized when dissolved in water. For example, ionic compounds, NaCl, copper sulfate, all of those ionic compounds are strong electrolytes. Strong acids as well, they completely dissociate. That's a definition that you could also use. They fully dissociate when dissolved in water. So for strong acids, note that when it's dissolved in water, it completely forms its individual ions. Completely forms hydrogen, completely forms chlorine. There is no going back. It only forms its ions. Similar if it were a base, sodium hydroxide would have formed sodium and hydroxide completely. When we're looking at weak electrolytes now, these are partially ionized when dissolved in water, right? For example, weak acids, weak bases. Weak acids such as ethanoic acid and a weak base such as ammonia. These are only partially ionized when dissolved in water. Right? Moving on.
And it's high reverse though.
It's a reversible reaction. What it is saying is that while we're forming the products, we're reforming the reactant itself. So at no point in time we're just going to have all of this forming. We're going to have both of these. That's why we say it's a weak electrolyte. Because this, I will cause it, the presence of this, I will cause it to not be able to conduct electricity. But these allow it to conduct electricity. And remember, at the same time, you have both of them for the reaction. Right. So it's a weak electrolyte. Yes. Alright. Note, solid ionic compounds do not conduct electricity as their ions are localized in their crystal lattice. They are not free to move, and I would have explained this already. If you were to throw this in some form of water, the ions would be able to move around freely. Now, earlier I had also said that water, yes, water is a covalent compound, but it's a weak electrolyte. So water being covalent, we do not expect it to conduct electricity. It doesn't have any free ions, no free electrons. It should not conduct electricity. You don't have no free. So water, as I said, it's a weak electrolyte. Yes, it is a covalent compound which only partially dissociates. Positive. Yeah, that looks like it. Yes. Okay, so the oxygen, remember oxygen in the covalent bond, oxygen has 2 electrons that it needs to share to become stable. Right? Now it's going to use one of its electrons here, one here. Hydrogen is also going to use 1 electron. Right? So oxygen is now full, hydrogens are now full. Now, how chemistry, I wouldn't say how chemistry works, but in chemistry, the compounds that are furthest to the left side of the periodic table, we call them electronegative. They are more likely to accept electrons than to gain. So they have like this very strong pull on them to accept electrons. Oxygen being furthest to the right, it is more likely to accept electrons. It has a stronger pull. So even in this bond right here, even in this bond, it is pulling the electrons closer to itself. It does not completely accept the electrons like in ionic bonding. It's just pulling the electrons closer to itself. When you pull an electron closer to yourself, what's the charge that you get? Or when you accept electrons at discharge? Negative. But because it did not completely accept the electrons, it gets a partial negative charge.
Does the stand for partial?
Yes. Gets a partial negative charge. And for hydrogen, because it did not completely give up all of its electrons, it gets a partial positive charge. This is what we refer to as a
Is it
polar.
an S?
It's not an X, it's like a half eight.
Okay.
Yes. It's like a half eight. This is why we say water is polar. So for polar compounds, you have, see me explain it now, what I had told you. So for polar compounds, you have uneven distribution of electrons in the covalent bond. Uneven meaning that the electrons are closer to one side. If it were to be a non-polar could be oxygen, O2. So you have oxygen, oxygen. Both of them have the same amount of pull, right? The same amount of pull. Both of them want the electrons. So it's almost like a tug of war where the middle part is stuck in the middle. So it's just going to be here. So we see that it's an even distribution of electrons. That's non-polar. And what you can use to remember this, for polar, just remember your poles, you have north pole, south pole, two opposites, right? But non-polar, you don't have any poles. It's just one of the same. Yes. And this is why water is able to conduct electricity. It only partially dissociates. It partially breaks up into its individual ions. I remember water can dissolve in itself because water. Yes. Note that when it's dissolved or when it's dissociated, only a small concentration of OH ions are actually produced. We don't produce that much OH, just a small amount.
So water can conduct, but it's not
a strong electrolyte. It can conduct, yes. So that's why when you put people get electrical shock when them drop them flat iron in the water and then they in the water. Or when rain fall on the wire.
That seems weird.
In a ceiling, so imagine something where strong.
exactly.
Imagine something where strong.
That's what I have to say,
Right.
Yes.
The plug-in stuff there, and the electrical.
And how like if you put the plug in and what like if water catch it, it's full of the hose. Short. Yes.
But that's why I don't understand why that is classified as a leak.
Gives like an
It is. See here. I'll show you. But you know, so when you do it in the lab, if we were to use like the ones in the lab, so for example copper sulfate, you wouldn't see it happening like you know what, you actually can probably see the electricity. Yeah, but for these ones in the lab, you won't see it because it's controlled. So we don't use such a high voltage like what they outside, what they use in other like this. If we were to use that now, these ones would cause much more explosive reactions, even worse than water. Yes. I am going to send a video on copper sulfate later because it's something you need to watch. It is coming. We don't know if I come on this one, but it might come. When we look at strong electrolytes, they fully ionize when dissolved in water. Weak electrolytes only partially ionize. And on non-electrolytes, these are substances that remain as molecules in their liquid state. Right? When I say molecules and I highlighted covalent, molecules are covalent compounds. Right? So these are substances that remain as their covalent structure, as their covalent compounds, even when they're in their liquid form or when they have been molten. Right? And they won't conduct electricity. Okay. For example, yes. Glucose, this is a good example. You might see a question that says, tell why C6H12O6 does not conduct electricity, but NaCl does. That was done in a lab.
So
I think lab 4, bonding lab. Yes. This is glucose. So they might ask you, why is it that glucose does not conduct electricity, but NaCl does? Remember, glucose is a covalent structure. covalent compounds do not conduct electricity because they don't have free ions or free electrons. NaCl will. Especially when it's dissolved in water. Yes, so we have glucose, sucrose, ethanol. These are all covalent structures. Ethanol would be C2H6O. That is our ethanol. Note again, all of these are nonmetals. Similar with the sucrose, and then we have molten covalent substances, for example, wax. It is covalent though. It is covalent. Liquids, for example, kerosene, gasoline, and ethanol. All of those are covalent, so they wouldn't conduct electricity. Alright, now we're going to look at the process of electrolysis. So we looked at most of the theory behind it, what conducts and what doesn't. Now we're going to look at electrolysis, which is the process of decomposing an electrolyte by the passage of an electric current through it. So the process of decomposing, breaking down the electrolyte when an electric current passes through it. That's the process, that's electrolysis. And this is a shorter definition for electrolyte, a molten ionic compound or solution which conducts electricity. Now, for electrolysis, it occurs in an electrolytic cell or in an electrolytic circuit, any one of those, and it includes, you have several different parts. So for one, it has the electrolyte. You have to have some form of substance that is able to dissolve and conduct electricity. You must have your electrolyte. Then you have your electrodes, right? These conduct electricity to and from the electrolyte. And you have two types of electrodes. You have your anode and your cathode. The anode is our positively charged electrode, and the cathode is the negatively charged electrode. The anode accepts anions while the cathode accepts cations. Right. For our power supply, this supplies electric current to the circuit. It can be a battery, right? That will be our power supply. And the batteries are so very big. So power supply, then we have a switch which is used to power on and power off the circuit. So we just look at the parts of the electrolytic cell. What we're going to look at next is actually putting those parts together in our electrolytic, or in our electrolytic process. So for one, as you can see here, I should have drawn this from scratch, so you can see how to do it just in case you're given. So what you draw first is your beaker. You have your beaker with your solution. The solution contains two things. It contains the water and the electrolytes dissolved in the water. That's what's in the solution. So if I write here, I'm just going to label my electrolyte. Electrolyte dissolved in water. Right? Next, we have our electrodes. We have our positive electrode called our anode, and we have our negative electrode called the cathode. So the positive electrode is the anode, the negative one is the cathode. The positive electrode accepts the negative anions, while the negative electrode accepts the positive cations. So as you can see here, anions go to the anode, cations go to the cathode. And we already know that anions are negative, cations are positive. So opposite charges attract to each other. Now, in addition to this, we have our power supply. Notice for the power supply, it matches the terminals, matches that of the charge of your electrodes. So the positive electrode is connected to the positive terminal. The negative electrode is connected to the negative terminal. If it were the other way around, no electricity would conduct. Yes. No one ain't go flow through. You have to connect. As you go to the battery, right? You put the positive to positive to positive and negative to negative. Same thing. Right? But remember that for here now with your ions, this one. Right. So let me just label this as our power supply, which is also our battery. and we also have our switch. Now sometimes if you want to record, for example, the amount of current flowing through the circuit, you might just add a voltmeter or an ammeter. That's soon. So let us go through it again. We have our beaker. With the electrolyte, right? We have our electrode, we have our anode and our cathode. The anions go to the anode, the cations go to the cathode. Then we have our power supply, which we can see the positive electrode is connected to the positive terminal of the battery, and we have our negative electrode connected to the negative terminal of the battery. We also have our switch and our voltmeter. Alright, now we're going to put this into perspective. We're going to look at the basic principles, what really happens in our electrolytic circuit. Now the first thing I wanted to know is that, remember I keep on saying, you have your solid, right? So we're using NaCl for example. We have our solid NaCl, we put it in the water, it dissociates. It splits into the individual ions, right? So it says electrolyte is placed in the cell, and it dissociates into its individual ions. So we form a positive and a negative ion. Before I even look at the other steps, I want you to know that at the end of electrolysis, the ions form their atoms. At the end of electrolysis, the ions form their atoms. So even without knowing all of this process, at the end of electrolysis, the ions form their atoms. So if I were to have, for example, Cu2 plus, at the end of electrolysis, it's going to become Cu neutral. That's what I mean by the atom, the neutral atom. If I had lead 2 plus, it would become lead, right? If I had Br minus, it would become Br neutral, right? Just remember, at the end of the electrolytic process, you're forming their individual atoms. And it would be in their standard states as well. So I believe this would have been solid, bromine gas, and Br gas will be Br2, lead, solid. Note also that when it was in its ion form, it would be aqueous. So if you don't remember any of this that I'm about to talk about, just remember this. You start off with your solid break up, form the ion, and then at the end of electrolysis, it becomes neutral. It becomes its atom form. As I said, first we start off with, we add our solid into the water, it dissociates into its ions. Once it dissociates into its ions, we're going to have some form of attraction happening. So we have our positive ion and our negative ion. The positive ion is going to be attracted to the negative electrode. The positive is going to be attracted to the negative electrode, and the negative is going to be attracted to the positive electrode. In other words, anions go to the anode, cations go to the cathode. Anions to the anode, cations to the cathode. And this one occurs first. The anions go towards the anode. Right? So after you splitting your ions, the ions then go to them electrodes, so form of attraction happens. The next thing, this is number 3, they are discharged and lose electrons to form atoms. So we're looking at what occurs at our anode now. As I said, that's the first thing that happens. Over this side happens first. So your anodes go to your anode, right? Now at the anode, note that we had our chlorine. We had started with our chlorine ion here. The chlorine ion is going to lose its electrons to form its atom. Even if you don't remember that it loses, you can think about this. It goes from the negative, it goes from its ion to its atom form. Right? Now, this, we know that the loss of electrons, we call it oxidation. So how would I complete this equation here? How many electrons are involved? 1 electron, where would I put that 1 electron? Over this side. So it's going to be minus 1e. Plus 1e. Plus 1. It's going to be plus 1e. Right? So remember oxidation, I'm going to just revise oxidation is the loss of electrons. We have one electron involved since we're going from -1 to 0. Yeah, that's not what we're talking about. But we're going from -1 to 0, right? Oxidation, that's just one electron. We're losing one electron. But we know that we cannot have negative signs in chemical equations. So to make it positive, we have to add it here and add it here. But when we add it here, it cancels. So it now just remains on the other side. The figure that I made on this, it's still an upload. Still, it's on YouTube, but it's still uploading. Or you can watch other videos, but it's online. Alright, so that's what happens at your anode. Has anybody been lost? We're here. Okay. So for the anode, right, your anions, they get attracted to the anode, right? And the anions, they lose their electrons. That's what happens. Now this is saying the anode, so remember the anions, they lose their electrons, you know. Therefore, the anode would be the one causing it to lose its electrons. So we call the anode the what? The one that causes it to lose. The one that causes it to lose electrons. Oxidizing agent. So oxidation, the loss of electrons. Oxidizing agent, the one that causes the other one to lose electrons. So the anode would be acting as the oxidizing agent. Right? So remember your anion, it loses its electrons. The anode accepts those electrons. The anion is undergoing oxidation while the anode is acting as the oxidizing agent. So I'm just going to put a little marker. So this is where we're at. We're going from here. We have oxy. This is acting as the oxidizing agent. And currently our electrons are here in our positive terminal. That's where we're at now. That's where the electrons are. Okay. Next, what happens is that the electrons, they travel from the positive electrode up to the positive terminal. So they're going around the circuit. They don't just go across, they have to go around. So they travel and go around to the positive terminal. It exits back out through the negative terminal, passes through the switch if a switch is present, goes around, and then goes to the cathode. So the cathode gains those electrons. Not only that, the cathode will gain the electron, yes.
Everyone, it will be, we gain one electron.
One electron.
Okay.
Alright, so it gained the electron, and after it has gained the electron, note that simultaneously our positive cations are being attracted to the negative cathode, right? And at the same time, these are going to be gaining the electron. So the cathode would have gained the electron, but it lost it due to the cations present. So the cations gained the electrons. Say come from here, say start over here. This year lose it, you come here, so this year get it, you go on, you go on, you go on.
Right, yes, I get it too.
This year get it too, but then once you get it, you just lose it and you go back to the next one.
Oh,
So instead of
That's
making,
circle.
so they're coming like one
That's
side.
circle.
yes, it does not, take shortcut none at all. It always go around. It goes around the circuit. Just remember that at the anode loses it first. The anode loses everything except until it reaches road over to accept the electrons. Right? Now when our cation accept the electron, so we accept the electron, what we call that? In what process reduce to accept electrons as reduction. Remember oil rig, oxidation is loss, reduction is gain, right? reduction is gain of electrons. So the cation, it would gain the electrons. Also, remember as I told you at the beginning, even if you don't remember all that, let me tell you, remember say, either your cation or your anion at the end of the electrolytic process, they're both going to become atoms, right? So notice I wrote this equation already. It would have been the Na going to become its atom. But we said that at our cathode, reduction occurs at the cathode. Reduction is the gain of electron. We're gaining 1 electron, so it's going to be plus 1 E. That would be it. Alright? And as it says here, the cation gains the electrons from the cathode. The cathode is the reducing agent. The cathode causes the cation to get the electrons, so the cathode is the reducing agent. Okay.
The anions travel up the anode, the negative anions travel up the anions in the battery to the positive, whatever is terminal, travels through the switch, if there is a switch, down into the cathode, and then it's transferred to the positive cations, then the positive cations release it. You know,
The positive cations get the electrons.
the electron.
Get the electron. Right. Something you missed, 2 things. So that's fine, but I want you to remember to mention what processes occur. So just state that oxidation occurs at the anode, reduction occurs at the cathode. And let me just say this before I forget too. How I remember it is we have A, vowels, right? We have rings in our vowels. Oxidation, AO, oxidation occurs at the anode, and reduction occurs at the cathode, or consonants. Oxidation occurs at the anode, reduction at the cathode. So that's something you should have mentioned. On that, you also have to mention that at the end of the electrolytic process, neutral atoms are formed. Mention that as well. So what you had said originally was correct. We need to remember the processes and also what the end result is. We're going to look at electrolysis in 2 types of electrolytes. We're going to look at electrolysis in A+ electrolytes and electrolysis in molten electrolytes. Now, for aqueous electrolytes, they are dissolved in water. Aqueous electrolytes are dissolved in water. Now, because it's dissolved in water, we're having several different types of ions present in the water. So, you know, if we put salt in a water, we have whole heap of things in there. We have NaCl and we have the water ions themselves. Similar, it's the same thing happening right here. Right? So we have, let's say it was NaCl. It would have been Na plus and Cl minus as our solute. Right. And then for the water, we have H plus and the hydroxide coming from the water, the H2O. Now, this water molecule, or the several water molecules, they do in fact the preference of the ion being discharged at either the cathode or the anode, right? So yes, you would expect say okay because the NaCl is the electrolyte, then therefore the Na have to go up to this, or the Cl have to go up to this. That's not always the case. Because you have the other ions present, those other ions might be preferentially discharged, they might be preferentially ionized, or reduced or oxidized at the individual electrodes. Right? And we're going to look at 3 factors that affect preferential discharge. Now, it says by definition here, preferential discharge is the preference of discharging one type of ion at either electrode. We're choosing to discharge, we're choosing to have one of them, one of the ions. So yes, it could have been that the Na and the H plus from what we have here. So these are both positive. these are both positive ions, both would be attracted to our negative cathode, yes, but one of them would actually be preferentially discharged. One of them would have come off, basically. You would have seen one of them react. That's what you would see. Not both of them at the same time, one. And it depends on three things based on the type of ion. Right? So the first one we're going to look at is for the first factors affecting differential discharge of our anion. We have three of them. The first one is the type of anode present. Right? And we have two types of anode. We have the inert anodes and we have active anodes. Right? So we have inert and active. So you might hear somebody say inert electrode, active electrodes. Now inert electrodes, they do not take part in the electrolytic process. Electricity passes through them, but they are not decomposed. Nothing happens to them. They don't react. Just that one electrical current goes through them. That's for inert electrodes. For example, we have platinum, mercury, and graphite. For active electrodes, these are ones where yes, electricity passes through them, but they themselves are being decomposed. Some form of, I shouldn't even say decomposition, but some form of change is happening with them. Some form of change is happening, right? So for example, we can have zinc, aluminum. These can be either reduced or oxidized. That's what I'm saying, right? So it can be zinc, aluminum, copper, nickel, chromium, and iron. Remember earlier I gave the example of, let's say we had used the copper electrodes. It's a copper solid. Electrodes are solid, but once electricity starts to pass through them in the electrolytic circuit, right, and we have our electrolyte, then the copper solid is going to become ionized to form Cu2+. So the electrode is in fact, it's active, it's reactive, as long as the electricity is passing through it. If it were an inert electrode, for example, platinum, nothing wouldn't happen to it. It would just conduct electricity. So no change will happen to it. For this one, note that while this is happening and we're having our copper 2+ ions coming off, the copper solid is going to become less and less and less. It's going to shrink. It's going to shrink because we have formed ions. Ions will come off in the solution, so the solid part itself will shrink. So you could have started off looking like a square, and then at the end of electrolysis, you look like one little rod.
So means the color of the solution gonna change?
Yes, it's going to change to blue. Alright, now the second factor that we're looking at is the concentration of the anion. Now if the anion is very concentrated in the solution, they're going to tell you. So if it's very concentrated, right, it is preferentially discharged. We have a lot of that ions present in the reaction flask or in the beaker, right? So therefore you're going to have that one being preferentially discharged. So for example, they might have given in the question, concentrated NaCl is electrolyzed. What this is saying is that you have a lot of, and we're looking at the anion specifically, concentrated NaCl. So it's saying that we have a lot of chlorine ions present, right? We have a lot of it, therefore it is preferentially discharged. And what they mean, sometimes they might mean something like this. So as you can see the concentration here, looking at it. Anybody knows why I have the OH here instead of anything else? Why do I have both OH and Br? Which I use Cl.
That's why amount present.
This number shows the amount present, but why do I have two ions? Because what? They're both negative charge. Alright, so remember it's in an aqueous solution, so we have both water and we have the electrolyte present. Both of them have their individual anions, so we have to consider both of these and we're looking at preferential discharge. In the question, they probably would say we have concentrated NaCl. This is telling us that we have more chlorine anions than hydroxide anions, so the one that is preferentially discharged would be our chlorine anions. Yes. If they would have said something like this, that the most stable one. The one higher in the series, the most reactive one, the most stable one. The ones lower in the series are the less stable ones and are more likely to be discharged. So the one with lower in the series is more likely to be discharged, and you're going to write the half equation for that one. So in the case of electrolysis, let's say we say that bromine ions are more likely discharged at our anion compared to the hydroxide, compared to the nitrate, right? So it would have been Br minus to give Br neutral. It's an electrolytic process, right? So if I say the lower in the series, the more likely it is preferentially discharged. Therefore, you have to write your half equation for that one lower in the series. Now, to summarize everything for factors affecting the anion, when you're looking at it, you have to consider the type of electrode first. Now, if your electrode, so let's say I'm going to, the example I'm using, have three factors. You have your electrode, you have your concentration of your anion, and then you have the position in the electrochemical series. First one you consider is the type of electrode. Notice that in the question it says concentrated sodium chloride in copper electrolyte, electrode. Even without looking at this, right? You have to consider the electrode first. That's the first one we consider. Since we have an active electrode, this electrode is more likely to be discharged at the anode. The electrode is more likely to be discharged at the anode, right? Now, let's say we did not have, and that would be the half equation that we write for the anode. Now, let's say that we did not have an active electrode. We instead had something like mercury. Right? So we rule it out, say we don't have an active electrode, so we wouldn't write a half equation for that one. Now we have to consider the second thing, which is the concentration of the anion. In this case, notice that we have concentrated sodium chloride, so the chlorine anions would be preferentially discharged. That's the half equation I expect you to write there. Right? Now let's say that it was not concentrated, nor we don't have any active electrodes. Instead they say dilute sodium chloride in mercury electrode. So we take out, say we don't have no active electrode, we don't have no, the NaCl is not concentrated. So therefore we have to consider the one that is lower, the anion that is lower in the electrochemical series. In the case of NaCl, remember that you will have Na plus Cl minus, and you will have H plus OH minus in the aqueous solution, right? So the one that is preferentially discharged, the one lower in the electrochemical series, would be this. So looking at it, so we have Cl and hydroxide. Hydroxide is lower, therefore it is preferentially discharged. So for factors affecting preferential discharge of cations, as I said, it's only one factor and it has to do with the position in the electrochemical series. Once again, the higher you are in the electrochemical series, the more reactive you are and the more stable you are. But the lower you are, the less stable you are, and the more likely you are to be discharged. So the one lower in the series is the one that you would write the half equation for, the one that is preferentially discharged. So the lower in the series, the more likely it is preferentially discharged. Goes for both of them. Just remember the lower one is the preference. If that makes sense. Now we're going to use these to make equations, and it kind of summarize what we did when we looked at group 7 elements and displacement reactions. This has some factor in it as well. So it says predicting reactions using the electrochemical series. As I would have mentioned earlier, the ones at the top, those ones, yes, so the ones at the top are more stable and they are more reactive, right? Now, let's up. Also, the ones further up are more likely to be ionized. Especially for metals, the ones further up are more likely to give up their electrons. For metals, further up, more likely to ionize, more likely to give up their electrons. Right? Therefore, we say that the higher metal is more likely to be oxidized. Remember, to lose, oxidation is the loss, right? So the ones higher up in the metal series are more likely to be oxidized, and whatever is being oxidized is the reducing agent. So we can also say that the higher ones in the series are also the strongest reducing agents. Yes. Right, now let us look at this example, and this is going to combine everything. We have zinc plus copper sulfate, and we're going to see what is formed. Now, remember, the one higher in the series is more likely to displace the one lower in the series. So we're looking at zinc, and we're looking at copper. Copper is bonded, it's bonded to something, right? It is lower in the series than zinc, so zinc are the one taking its place. Remember why I think I used the example of the one that is prettiest, the one higher, the prettier one I will take, right? So what we're going to form is going to be ZnSO4. Note that zinc, the one higher in the series, is the most stable one and the more reactive one, so it's ionized. So we form an ionic compound right here. Zinc is ionized to its 2+ form. Right? Compared, matter of fact, before I do that, what would we have left? What would come off? So the copper is going to come off. It is going to be discharged. So this is actually the half equation that you would put at your cathode. The one for Cu2+. Yes. So it would be Cu2+ to give the neutral copper. Yes? So the one will come off by itself. The lower it is in the series, the more likely it will be discharged. The one higher in the series, the more reactive it is. It will take something and bond with something. Let us look at this one. It's very similar when we're looking at acids, right? And we know this equation. Once we have a metal reacting with an acid, we're going to form what? Metal and acid, salt and what? So look at the trick, easy. Metal and acid give you salt and hydrogen gas. Acid plus base, salt and water. Acid plus metal, salt and hydrogen gas. So we're going to form our salt here, but let us look at it in the series as it relates to the series. So we have our Na and we have hydrogen. Hydrogen is lower in the series than Na, so therefore Na is going to take its place. Na is going to displace hydrogen. So we are going to form NaCl. That is our ionic compound, NaCl, right? So Na is ionized here. Will be Na+, and we have hydrogen ions being discharged. So this would be the half equation that you write for your anode. Right? That would be it. Now for non-metals, it's very similar. The higher they are in the series, the more reactive and the more stable they are, and the lower they are in the series, the more likely they are to be discharged. So, looking at this, what do you expect? So we have two non-metals, chlorine and iodine, which is higher in the series. Chlorine is higher in the series, so the chlorine is going to take the potassium, is going to be KClAQ. That's that. Alright, and then our iodine is going to be discharged in its elemental state. writing our half equation for the one that is preferentially discharged. In this case, it's for the iodine. Iodine over this side is bonded to something. It has a 1 minus charge. Over this side is elemental state, it's neutral. So our half equation is going to include I minus to give I neutral. Right? Now we are going down our number line, going from -1 to 0. So that's reduction. Reduction, and we're going down one time. Reduction is the gain of electron. We're gaining 1 electron. So it's going to be plus 1e. However, to balance it, notice we have 2 iodines on both sides. So both are going to be multiplied by 2, similar for the number of electrons. So therefore, our overall half equation is going to be 2e minus. That's going to be our half equation. Note that we could also write the chlorine half equation as well. It could also be Cl neutral to give Cl 1 minus. Right? Notice that what's happening? So it's going from 0 to 1 minus, that is what?
0 to 1 minus.
Reduction or oxidation? Yes, it's reducing. It's going down. Down?
Yeah.
Yeah, down. You can feel I need to draw it, you know. Maybe I should draw it. So we have plus 2.
Negative sign,
Yes, it's going down. It's going down, down, down. So that's gonna be reduced. Reduction is the gain. We're gaining 1 electron, so plus 1e. Plus 1e. To balance it again, we have 2 chlorines on both sides. So it is gonna be 1 times 2 equal 2 electrons. Know that if we had started with 2 electrons, right, and we needed to balance with 2, it would be 2 times 2, which would give us 4 electrons. So, to balance, you multiply the electron number by the amount of atoms present. Now, once again, the one lower in the series is more likely to be discharge. Therefore, the half equation that you should have would be this one. This equation suggests that iodine is more preferentially discharged compared to chlorine. The last thing we're looking at is the electrolysis of molten electrolytes. So we looked at the electrolysis of aqueous electrolytes, which are, yes, Jessica?
Continue.
The video for this is uploaded. I think it should be finished now, so you can watch it when you go home. Yes, because we covered all of that yesterday. Alright, so, right, for aqueous electrolytes, those ones are dissolved in water, but for molten electrolytes, they aren't. And the example I'm using is that, for example, you have molten lava. It's almost like the solid form, it melts. It's in its molten form. It's not in water, it's just melting, right? So in this case, in the electrolysis of molten electrolytes, it's just the electrolytes alone we have, right? Now when it melts, it splits to form its individual ions. See it here? When it melts, it splits to form its individual ions. So we have lead 2 plus and Br minus, which forming the ions. Okay. Now, what happens when we pass electricity through a substance? Based on what we did before, when you pass electricity through it decomposes and forms what? So it was originally the ion. When you put electricity through it, it forms what? The neutral state, and that's the same thing that's gonna happen here. So we have our ion going to form its neutral, right? Same thing what's happening over here, the ion going to form its neutral one. Now let us complete our half equations. We're going to complete our half equations. So over here with the lead, what's happening to the lead? It's going from 2 plus to neutral. Reduction or oxidation?
Reduction.
It is reduction. How many electrons are involved?
How many what?
How many electrons are involved? 2 electrons. Reduction is the gain of electrons, so therefore it's going to be plus. Over the next side, looking at bromine. Right, looking at bromine, we have Br 1 minus going to neutral, oxidation or reduction. Oxidation is going up, right? How many electrons?
It's going up by 1.
1 electron is going up by 1, so it's 1 electron. Oxidation is the loss of electron, it's going to be minus 1e. But remember, we can't have negative signs in chemical equations, so we have to get rid of it by adding. To be able to one side, do to the other side, so this would cancel. This would cancel, and that's what we get. Remember as well that when you're writing your half equations, you have to make sure that you have the same number of electrons on both sides. So let's have gain 2 electrons, right? So therefore, bromine have to somehow involve 2 electrons. You could have choose to just multiply it by 2, or even looking at it, notice originally we had 2 at the top. So to balance it would be a 2 here and a 2 here. You also have to multiply the number of electrons by 2. So it becomes plus 2e. And that is balance. Thank you for watching. That's it with Miss Wallace teaches chemistry.
Chemistry.